Good morning. Pleasure to welcome everyone back for the second day. And our first speaker is Mike Freedman, and it's a great pleasure to say his affiliation, which is CMSA at Harvard, and his title is ML, QML, and Dynamics.
Thank you, Dan, and it is a great pleasure to be here, and congratulations to Dan for taking over the CMSA. I'm very excited to have a small part in it. I'm very excited to be here. So I don't know anything really about machine learning or quantum machine learning. In fact, I'm not sure anyone knows anything about quantum machine learning. But I've been thinking about it, been obsessed by it in some ways, trying to understand it. So I have tried to identify some mathematical issues that maybe are worth sorting out. And I've talked to a number of the practitioners like ChatGPT and Bard and other places. And they're all drinking the Kool-Aid, I mean, they really believe they have it down. And the sub-theme is they probably don't need much help from mathematicians. That's what they think. But there may be still some things to do. It may not be an exponential curve in power of these AIs indefinitely. There may be some new ideas that are necessary. So I think there may be some work for us to do as mathematicians. But maybe not. Maybe they have it all under control. So if you just take your basic vanilla deep neural net, it's very reminiscent of old stretch and fold dynamics, which is a subject I was sort of raised in. This is has names like Feigenbaum and Smale associated to it. Because what a deep neural net does is it has many layers. Like in some applications, you might think 80 layers or 100 layers even. And information input is propagated through it to output. And in between the layers, there are linear maps, followed by coordinate-wise nonlinearities. And the linear maps have to be tuned in order to avoid blow-ups or crashes, sort of amplitudes to zero as you propagate through. So you should think of them to a first approximation as like hyperbolic transformations. They have some expanding and contracting directions. Maybe the determinants are kept rather close to 1. But then they're followed by, like ReLU or other threshold called activation functions that can be extremely simple, like 0 for negative, identity for positive, or they can have various valleys and dips in them. And absolute value is a perfectly good nonlinear function, for example. And if you think of that as your nonlinear function, then you really do the analogy with one-dimensional dynamics, stretch and fold, Feigenbaum's discussion of powers of logistics map. So there's evidence, and I'll just show you a few snapshots from some papers, that this sort of onset of chaos that was very familiar from the story in the 60s and 70s about iteration of these stretch and fold maps. This onset of chaos probably has something to do with trainability of networks. So a fundamental example, this logistics map, I reproduced the equation. So this is iterating a quadratic equation. And I think the pictures are from Wikipedia. If you start with a quadratic function and you look at its higher powers, you get these successive ripples. And the figure below is the dynamics. It shows this bifurcation where you have a fixed point breaking up into a point at period 2 as a parameter is varied. That would be the R parameter in this logistics equation. and then period 2 breaks up into period 4. Then it's harder to see it, but period 8. And the ratio of these bifurcations is this famous 4.6 ... number. That's the universal thing. That's the Feigenbaum. And then at the limit, it becomes chaotic, and then there are resurgences, and there's all this, story of the transitions to chaos, Pamu-Manville scenario where you have regions of laminar flow and then chaos and back again, intermittency. This famous theorem that period 3 implies chaos, York and Lee. So there's this marvelous set of stories from the 60s and 70s, and there is a difference in the neural net. You're not taking powers of the same map. These are different stretch and fold maps between the layers, where to simplify in classical dynamics, you take powers of the same function. But that's an important difference, but I don't think it's dispositive. I think that there's still a lot of very much a lot of structure in common, even if the function is varied between the layers. So I think that there's much that can be learned by going back and thinking about the dynamics from that era. A very favorite example among topologists, because unlike the one-dimensional stretch and fold maps, this map is invertible and you can go backwards in time as well as forwards in time, is the famous Smale horseshoe, where it's a diffeomorphism of the plane, which takes a square and stretches it out in this picture by a factor of about 5 or 6, and then it folds it over, kind of like absolute value, and places it across the source. And then if you iterate, you see 4 strips going across the source horizontally. And if you kept going, it would be powers of 2, more and more strips. Going forward, you'd see a Cantor set worth of horizontal lines in the forward limit. And if you iterate backwards, you get, in the limit, a Cantor set of vertical lines. And the invariant subset is the intersection of the vertical and horizontal sets. And that's a Cantor set in the plane. And it has this very beautiful symbolic dynamics where the address of the points in the Cantor set tells you, is predictive of their forward and backwards behavior. So you have periodic points in the Cantor set of all periods, and points that are not periodic and whose dynamics is chaotic. So I want to now just delve even farther back into the past. That was math of the 60s and 70s. Let's go back to the 1950s. There's a theorem which I think it's legitimate to call amazing, because when you read the statement, you don't believe it. It's the definition of amazing. So this is work that was done. It was actually V.I. Arnold's first mathematical work. I think he was like a 19-year-old graduate student of Kolmogorov when he made the breakthrough on a problem that Kolmogorov was thinking about, which is Hilbert's 13th problem. I didn't actually put Hilbert's 13th problem up on the screen. It's a little bit beside the point. It's kind of curious, though. He expressed it as something about 7th degree polynomials. And I was talking to Kurt McMullen yesterday, who pointed out that he could have phrased the problem also about 6th degree polynomials, but it was more convenient somehow, 7th. But the basic question was, someone from the 19th century had figured out how to zero out 3 of the coefficients. So with change of composition of radicals, sort of like the usual formulas for low-degree polynomials, you can put it in a form where it's monic, and then there are like 3 zeros. And then Hilbert's question was, okay, now the roots are moving around just locally, say. The way a root moves is a function of these other 4 variables. And he was asking, could you hope to simplify this and make give an expression where it's moving as a function of a smaller number of variables, and then like add those together, and then another function of a small number of variables. So if you look at something like the quadratic formula, or the way to solve a third or fourth degree equation by radical, you do some successive work with functions, each of which is only of one variable. And Hilbert showed that this, by dimension counting, basically, which is a natural guess, that this is impossible for analytic functions. You don't expect to be able to do the work of an analytic function of many variables with several analytic functions of only one variable, because it kind of looks like there aren't enough of them, and that intuition is right. And it was later proved for smooth functions, C infinity, even C1. But it turns out that through work of Kolmogorov and Arnold, it's false when you go to continuous. And the continuous doesn't even have to be that bad. It turns out that Lipschitz is sufficiently non-smooth for this to work. So let me read this statement. So the statement is that if you're interested in the n cube for n greater than or equal to 2, so just focus on the square, n equals 2, then there are just 2n plus 1, so 5 continuous functions fixed once and for all, which you can actually think of as together, these 5 continuous functions would be an embedding of the square into 5 space. And then what it says is that after that, given any function on the square of the n variables, then it can be written as a sum of functions on its coordinates. See, these are the 5 coordinate functions as I sum from q equals 1 to 2n plus 1. So it says that the general function, let me just use the square for n. The general function on the square can be written as a sum of functions. When I say functions, these are continuous functions. The general function on the square can be written as a sum of functions on its 5 coordinates after this embedding. So the embedding's fixed. You have a general function on the square. You come up with these 5 functions to apply to its 5 coordinates. Add them together, and that's the original function. That's what the formula said. And then
Given f, are you allowed to vary the 5 or
just alpha. The embedding is fixed once and for all. And it turns out there's nothing special about the large-scale structure of the embedding. The embeddings that work turn out to be dense. So it's only the fine detail of how you sort of rat your hair or something. It's like a little bit of style that you add to your embedding. And this was, I'm sorry, I think I forgot to put the credit. I'm sorry, it's perhaps on a later slide, but in the late 80s, computer scientists became aware of this theorem and noticed that it could be used to say that a 3-layer neural net is completely expressive of continuous functions. So that's illustrated in this little 3-layer network. That is, I want to produce a general function on, say, 2 variables. Then I can transmit those variables into 10 intermediate nodes. So just recopy the variable 5 times. That's, and then apply the coordinate functions, and then apply the outer function to get the function of 2 variables. So what this says is that neural nets of very small depth, only depth 3, are completely expressive. But in order to express them, you have to have these very complicated nonlinear functions, alpha, stuck in at the end, much more complicated than ReLU or absolute value. So there's a trade-off. Expressibility occurs very early in the elaboration of neural nets if you're willing to have extravagant nonlinearities here at the end. If you only have simpler nonlinearities, you'll have to take deeper nets. And then another thing to keep in mind is this theorem only has to do with expressibility, which functions can be written in this form. But the interesting thing in computer science and AI is trainability. You want to know whether you can iteratively, by gradient descent methods and backpropagation, whether you can find the linear and not find the linear maps which realize the function you're looking for, and the function you're looking for is some discrimination function on the input, often like cat versus dog. So you should keep in mind that there are two separate questions, trainability and expressibility. A beautiful, so I was kind of oblivious of this whole area of geometry and topology. You know, it's funny because I think of myself as a fairly broad geometric topologist, and that, you know, I got into my 70s without knowing about Kolmogorov's work. I was a little stunned. It just shows, you know, one doesn't go to all the conferences or all the sections in the AMS meeting. So this Kolmogorov Arnold stuff percolated along, and this is a beautiful statement from the late 80s. Half the implication is due to Ostrand and half to Sternberg in different papers, but if you put it together, it says that it's actually a criterion. A compact metric space has dimension n, which is a covering property. If and only if it can be embedded in 2n plus 1, which is the general position embedding space, dimension for complex. And we'll call that embedding x goes to y, which is basic. And the meaning of basic actually is what I was talking about on the previous slide, but here it's written out. An embedding is basic if every function, one variable function function into the I. You should think of this as a multivariable function because x is n-dimensional. If every function on x can be written as a sum of functions on its coordinates. So that's sort of what I had on the previous slide, except I had the coordinates explicit in terms of the phi's. The sum before was also to 2n plus 1. There's an outer sum here. Yeah. So, you know, this is a beautiful characterization, and I think that so this was noticed, as I mentioned, in the late 80s by people in the field, but it was more or less dismissed. There's been very little discussion of it in the last 25, 30 years. And I think it was dismissed because it was thought to be not numerically useful. I mean, since this phenomenon doesn't work for smooth functions, it only works for kind of wild functions. In order for this to be a useful tool, one should prove quantitative versions of it. It's not enough to say that you can express any continuous function. You know, what you want to do is, if you want to express the function to a certain fidelity, you should want to know how accurately you have to prescribe this embedding and how carefully you have to choose these functions of one variable alpha, the functions of the coordinate. So I think this is just begging for quantitative versions. So that's my first math problem. And I think I said it here, that the inner and outer functions have been regarded as too pathological to train, and probably that is true, and that maybe Kolmogorov Arnold, Ostrand, Sternberg should be generalized. You know, that this empirical discovery of the computer scientists that a lot of that deep is good should probably be exploited in this mathematical discussion. We should probably think of iterates. So now let me move a little closer to the present world. So there's a paper by the authors I mentioned. I think it's mostly a Google group from 2016, where they considered the differential geometry of evolution of data under random nets. So they didn't train the net at all. They just chose the matrices that connected the intermediate levels, Gaussian random, independent for each entry in the matrix. And there was a regime that they studied. This sigma is the variance of the entries of the weight matrix, so the linear map. And this WB is or sigma B is the offset. So I called these linear maps, but they're really affine maps. They have a constant offset. And constant offset means that the map is sort of doing the same thing on all the neurons. So that's like giving the neural network a sedative. If you have a constant offset, it's like you're pushing everything in the same direction. There's less discrimination. You're not differentiating. So it turns out that this ratio is an interesting thing. And when it becomes large, initial data, in all these pictures, initial data was put into like a 100-dimensional space as a circle, like a circle in a randomly selected two-plane. And then the neural net evolved the coordinates of the circle at random. And then this shows what the circle looked like in a typical three-space cross projection after 5 layers, 10 layers, 15 layers. So when you look at the top row, the circle kind of behaves itself. It's just sort of moving in some slow, smoothish way. And that's where you have a large offset and a small weights. But when the weights, so these numbers, the offset was fixed, and as the weights increased, as you go down, you see what they describe as chaos, that the thing gets twisted all around as it evolves through the net. And this circle is just, sort of a random marker to picture what the neural net is doing. It's nothing special about that circle. And this leads to the question, that crazy embedding that the circle is taking in this 100-dimensional space, it actually kind of looks like simulations of this Kolmogorov Arnold embedding. It's getting nice and wiggly. So that's a question. Is it doing this? Is it converging to a basic embedding? Basic meaning it has this amazing coordinate property, a property of representing functions. And what does this have to do with trainability? If it's converging to a basic embedding, that means expressivity is achieved, but what about trainability? And something I think we want to learn is what are the signatures, what kind of chaos, what kind of wiggling of this embedding, what kind of differential geometry is associated with the ability to be trained. That's maybe the most important practical question. So before leaving this little segment, I want to introduce just a conjecture of my own, and it's extremely rough. I'll call it the lapse conjecture, because in classical dynamics, they count, like one-dimensional dynamics, they count the lapse as the number of segments of the function that are monotone up or down. So it's how many times it does that. And this is important in the stretching and folding world. So the very vague thing I'd like to conjecture is that there's kind of a conserved quantity, which is the depth of the network times the logarithm of something like the lapse. I put in one there for safety. I'll mention that. So a way to think about this is it's the logarithm of the number of, this total expression is the logarithm of the number of layers of pastry. Because, when they make French pastry, they roll out the dough and they put in the butter and they fold it over. So that's the stretch, and more butter, and then the fold. And then the butter keeps them from fully readhering. So when you cook it, you get that. And you can see how many layers there are. There are 2 to the n layers. But if you did a more elaborate fold, if you had a more elaborate activation function, nonlinearity, then you'd triple the number of layers, say, every time you flattened it out and folded. So this quantity I wrote down here is really the logarithm of the total number of pastry layers. And it's that number of pastry layers that I think is related to expressivity. So here's like 1 lap, 2 laps, 3 laps. Now I told you this is a very vague conjecture. See, if you only have 1 lap, you can still, like ReLU, you can still express stuff. And logarithm of 1 is 0. So that would shoot the conjecture down, so I added 1 there. That's the only reason. But you know, if you think about like the Smale horseshoe, the fact that a first nonlinearity doesn't completely turn anything around doesn't prevent a composition of them from folding something around. See, like in 1 dimension, it would. Like if you're just working in 1 dimension, if you compose monotone functions, they always stay monotone. So you can't ever fold unless you bite the bullet and really fold at 1 step. But that's not true for like a diffeomorphism of the plane. As you can see with the horseshoe map, you could bend the horseshoe around very slowly in 5 different compositions. So anyway, that's just a detail. That's where the +1 came from. So I just think, so I actually talked to some of my friends who are actually working in AI about this conjecture and got a little bit of encouragement that they might test it at one of the companies. So there's another even more recent paper, so now I'm getting up to almost this year, from another group, mostly Google, it's called the power of data in quantum machine learning. But this is actually an interesting paper to try to kind of get some reality checks on what a quantum computer might or might not be good for in the machine learning domain. So if you consider the resources that are available, you know, one of the things you do in any AI model is you have to embed data. So for example, in large language models, the tokens, which you can think of as the words in a sequence, are put into some token embedding space. And a lot of the training has to do with moving these tokens around in the space so that they represent their appropriate relationships. So that, you know, words that relate to the same thing, like run, sprint, jump, or something, they sort of move near each other in this perhaps 1,000-dimensional space. That's you don't move them there by your choice. You know, that was like the old school where you try to think and help the computer. You know, it moves them all around by looking at trillions of bytes of data. So in classical world, though, these vector spaces that you embed things in are going to be limited to around 1,000 dimensions. And that means in order to solve problems, you have to do a lot of nonlinear dynamics in that space before you use a linear separator. The last thing you'll do is you'll draw some hyperplane in a space, and you know, to the left will be dogs and to the right will be cats or something like that. You'll make a decision, but if the space is only modest dimensional, you can't expect to have a good separator until you've pre-processed the data nonlinearly. Now in the quantum world, the situation is quite opposite. If you had 1,000 qubits, you'd be embedding into a space of this size. And this, for example, is exactly what you'd get if you used what they call amplitude embedding. So suppose you had a picture with 1,000 pixels, each of which was black or white. You could use that as ket 0 and ket 1 and a qubit for each pixel. And then each individual 1,000 qubit photograph would be its own basis vector in this space. And any 2 sets of them which didn't overlap could be separated by a linear separator. So no pre-processing. So that's one of the things people think is quantum machine learning, maybe you don't need pre-processing. You don't need nonlinear dynamics. You just separate directly. But what this power of data paper does, it sort of explodes that myth. There are many caveats that have to be discussed in connection with that story. So first is there's classically available to us in machine learning the technology of reproducing kernels. You don't actually have to take extraordinarily high dimensional spaces and represent states as vectors in these. Instead, you can simulate this, but you can reproduce an inner product on a Hilbert space by integrating a kernel. So there are workarounds that a classical computer can be done on a classical computer. And the other is the practitioner should have a healthy skepticism of dimensionality. There's a saying among numericists that if someone tells you that their data set is intrinsically n-dimensional, they better have at least two to the n data points in it for you to believe them. So the prototypical example is to consider in your mind the n cube versus the n simplex. So the n cube, if you just know it because of its vertices, that's 2 to the n vertices, and that legitimately is n-dimensional. Whereas the n simplex is definitely an imposter. It has n plus 1 vertices, and in terms of its distance relationships, there's no way it's really n-dimensional. Because if you squash it just randomly down a dimension, you'll change distances only the tiniest amount within the measurement error of your data set. So it would be silly to describe it as so high dimensional. And this is the concrete version of this. Lindenstraut says if you, it's actually stronger than what I've written here. If you take n points and you embed them in a very high dimensional space to achieve a certain distance relation, then what Lindenstraut proved is that if you take a random projection, you can take a random projection into little n dimensions so that the distances are multiplicatively changed only by a factor of 1 minus epsilon. Yeah, capital N points. Did I write lower? Yeah, so if you have capital N, there's a capital N and a lower n. So if you have capital N points, the number of dimensions little n that you need to express their distance relations is basically the log of capital N. That's what this is saying. Oh, I'm sorry. I didn't. Yeah, you're right. That's a typo. Thank you. So the psychological import for machine learners of Lindenstraut's theorem should be skeptical of the need to go to very high dimensions to extract geometric relations, and therefore slightly skeptical of the benefits of quantum Hilbert space. If you're going to say, oh yeah, we need c to the 2 to the 1,000 in order to express the geometry here, that's not, that's the advantages will have to come from something else. So those are the caveats. If quantum is going to help us in machine learning, it's probably not enough to say, oh yeah, it's a huge dimensional space. There's a lot of freedom. We can just use linear separators. It's going to be a more interesting story than that. So now, it's definitely true there is a path outlined for quantum to help machine learning, but it's not the kind of quantum that will be accessible to us in the next 10 years. If you imagine a world where quantum computers are fully operational and error-corrected and mature technology, then we do know from work of Seth Lloyd at MIT and others that there are speedups, important speedups, just in doing linear algebra under certain assumptions, conditioning assumptions about the spread of the eigenvalues. And these may be useful in the long term, but they're not going to be useful in the next decade or two. So I want to explore, what kind of math, what kind of thinking might be able to get quantum into the game earlier. So if we believe that chaos is the key to machine learning, to trainability, and there's some evidence of this, and I showed you one from that 2016 paper that there is a lot of evidence that networks learn sort of at the edge of chaos in some sense. then one reason for thinking in quantum language is it gives us a second way of understanding chaos. So up to now, the way I introduced chaos to us was through the stretch and fold maps, Smale horseshoe, homoclinic points, strange attractors, periodic orbits. There's that whole classical side of the picture, but then there's the quantum side. Remarkably, there's an interpretation of chaos within quantum mechanics, which superficially looks very hard because quantum mechanics is linear. So how can it describe chaos? But on the other hand, if you believe that quantum mechanics is the description of the world and classical world is a limit, then if chaos is in the classical world, it must have some relative in the quantum world, which is should be accessible to us. And quantum chaos is something that we can definitely explore on early quantum machines. And possibly they could be used to produce the right kind of chaos as input for classical neural nets. So in other words, quantum experiments might be useful in deciding how to train classical neural nets is sort of the theme. And a concrete example of this bridge between classical and quantum chaos is this phenomenon of scarring and the Gutzwiller trace formula. The Gutzwiller formula is, it reads kind of like an echo of the Selberg trace formula, and it's from the 70s, whereas Selberg was from the mid-60s. And I'm not sure if they knew about each other's work. Gutzwiller's paper does not cite Selberg, but I've been curious. But I wrote down the Selberg's version, and it is similar. So first, the picture. This is a picture from Wikipedia, and it has to do, what's drawn here is the amplitude of some eigenfunction in a potential. So there's a slightly irregular potential with, I think, actually, I don't think, maybe the potential is not, actually, I think, sorry, I didn't copy the legend, but I think this is a radial potential of fifth power or something. And the dark is where like the eigenfunction is intense and light is where it's small. And it's just showing the relationship between an eigenfunction and a classical orbit for the corresponding classical system. So this is general kind of picture is called scarring, and it's a phenomenon in its simplest case in single particle quantum mechanics that the intense regions, strong amplitude of a quantum eigenstate tend to concentrate around unstable classical orbits. And this is expressed here. Both of these trace formulas, what they do is they express some function of the quantum spectrum of the system, so the eigenvalues, in terms of some sum over orbits of some action. So what we have here is the resolvent of the quantum system, trace. So this spikes at eigenvalues. And this is the semi-classical version. That's what's captured by the formula. It's sort of a one-loop expansion of the action. And you sum over closed orbits over the infinite number of times you can retrace the orbit of some prefactor, which blows up when the density around the orbit is small. This is this chi is some measure of the way the monodromy, as you go around the orbit, it's a measure of how that expands. One minus the determinant of one minus the monodromy matrix. And then this is the action at a given energy, the same energy here. And this curious alpha thing is offset from focusing called the Maslov index. So there's these beautiful relations, but I think there's a lot of mystery still in this subject. For instance, there's this hypothesis that you can tell chaos on the quantum side by looking just at the bunching of eigenvalues, whether there's eigenvalue repulsion or not, but that seems too simple a story. That's definitely not the whole story. Yeah, exactly. The correct way of going back and forth, it's like there are these two windows on chaos, and they talk to each other through some beautiful formulas, but my suggestion here is a little bit vague, but it's that if we're going to understand these neural nets from a point of view of chaos, we should probably think about chaos, both classically and quantumly. Yeah, so in terms of experiments that can be done on a quantum computer, I think there's a nice phrase, active matter, which includes the papers on subjects like measurement-induced phase transitions. You have something unitary going on, and perhaps you randomly are making measurements, and there'll be some threshold when the frequency of measurements is sufficiently, when there are enough measurements being made, the growth of entanglement will all of a sudden drop. There'll be some phase transitions. So the system may be like approaching some chaotic regime, but if you measure, you sort of, it's like taking the lid off the pot. It's not going to get chaotic and wild as quickly. That's like the simplest thing you can do, this measurement-induced phase transitions, but you can also feed back on the measurement. So that's a kind of drive. People have studied topological phases in the presence of periodic drives. That's kind of Floquet. That's sort of the dumbest drive. That's just not looking at the system, but you can imagine a hybrid where you measure the system and drive it according to what you measure. And that looks very interesting and little explored in terms of the phase diagram and what you can achieve. But one extreme end of that is highly developed, which is measurement-only quantum computation, because that's an extreme form of measuring and reacting to that measurement and then doing the next unitary. So there's a whole regime in there, and the reason I point out that regime is if one is looking what can one do in this decade, before we have quantum computers that can be pushed into the regime where they can actually carry out computations, we can use them to explore like the statistical properties of systems that are being measured and reacted upon. And this is a way to perhaps generate reproducibly different types of chaos that we could explore in the machine learning context. So let me offer two slightly more concrete suggestions about what could be done with what mathematicians might bring to large language models. So the first one is large language models have all these matrices in them. I mentioned the W matrix and deep neural nets. These are the standard letters for transformers, query, key, value. I won't go into exactly what they are. But just think of AI as just full of matrices. And they're all highly trained. They're not, you might do an experiment with random matrices, but in the actual nets, these matrices are supposed to reflect the human world. Like we fed like half of everything that anyone's ever written down into this, and then optimized a bunch of stuff like predicting the next word. And then somehow, human culture and experience is now reflected in these matrices. Do they have any structure, or is it just a bunch of junk? It's probably mostly a bunch of junk, but can we find some structure in them? And I want to digress a little bit to a story. Just mention very quickly, some of you may have heard me talking about this in the past, But with collaborators, Moj, Sokri, and Zinni, and then at the end, for the last paper, Adam Brown, we found that by minimizing certain loss functions in a kind of physics setting, sort of a high energy physics setting, that the minima had structure that was quite remarkable, that we found that when we took functionals, for example, that minimized scalar curvature, at the minima, tensor decompositions emerged. So the example here is very often we would find that if we minimized a functional, and scalar curvature was an example, but not the only one on SU8, that all the principal axes of the metric, so I wrote 63 here because SU8 is 63 dimensional, and if you think of a geometry on it, Gij, that can be pictured as an ellipsoid of 63 dimensions with respect to the killing form. You have to have like a reference metric to know what the principal axes are. And what we found is that often the eigendirections, when thought of as 8x8 Hermitian matrices, were actually tensor products of 3 2x2 Hermitian matrices, all 63 of them with respect to a fixed isomorphism between 2x2s to 3 of them to 8x8s. So this is something that would never happen by chance, and it's an example of how when you minimize an interesting functional, you might see that the solution has a lot of symmetry. This is perhaps like a lattice. If you pack things to minimize energy, well, they pack into a crystal sometimes. So I mentioned this sort of high energy story to ask whether there's an analog in machine learning. These trained matrices, we could ask, well, might we see something like a tensor decomposition? Could the matrix W turn out to be W prime tensor W W prime? So the way we studied this, or the way we're looking at this, is if you have a linear map between inner product spaces, let's just suppose the inner product spaces have non-prime dimensions, so we factor them, and then we can ask, among all possible ways, of writing this space as a tensor product of 2 other spaces, and this space, the target space, is a tensor product of 2 other spaces. We could ask, what the tensor rank of the original linear map is. So that means, and the remarkable thing would be if it turned out to be rank 1. So what I mean by rank here, what would rank 1 mean? It would mean that this linear map actually was the tensor product of a linear map from some, say, A to A prime and B to B prime, and you just tensored, from A to B, A prime to B prime, and A double prime to B double prime. And if you just were able to achieve this original linear map by a tensor product, that would be rank 1. And this is quite distinct from the usual notion of the rank of a matrix, which is the tensor rank across a different organization of the tensor products. I mean, any time. Yeah, I mean, I'm just pushing around symbols formally, but the point is the high school definition of rank of a matrix, is tensor rank with respect to it's how many terms are needed to express that matrix as A star tensor B across that tensor. But if you have tensors of Hom spaces, then there are several ways you can organize the tensors, and you can point to any one of the tensors in the organization and ask, with respect to that tensor, how many terms do you need? So there's several ranks that can be discussed. And a group of us is looking for, Mason Barkeshale and his students at University of Maryland, is we're looking to see for some of these matrices that we get the data from Llama and other models to see whether these matrices have small rank decompositions, if they have special structure. And I don't have answers yet to report. I want to make a curious connection to the original discussion that I started with, this Arnold-Kolmogorov theorem. So if you have an array of real numbers, and the way to think about the real numbers in this example are the logs of the singular values of a matrix. So let me just step back a moment. If you want to tell whether one of the linear maps that arises in training a neural network, if you want to tell if it's a tensor product of two other linear maps, well, one thing you could look at are its singular values. You could look at its singular values and ask, are these singular values achieved as the product of two sets of singular values from possible factors? And that's actually a rare circumstance. It's rare that like n squared numbers taken at random could be the pairwise products of two sets of n numbers. And if you talk about the logs of the numbers instead of the numbers themselves, then of course you're talking about whether you can make them by pairwise addition instead of pairwise multiplication. And very curiously, this problem of pairwise addition, which sets of numbers, like 4 numbers, can be made by pairwise addition of sets of 2 numbers, this actually is what you think about in the dual approach to the Kolmogorov problem. The dual approach is trying to construct measures. So imagine this. This set of numbers is kind of a counterexample. This set of numbers, 1 occurring twice and -1 occurring twice, that can't be realized as the pairwise sums of any two, as you can find just by writing down the 4 equations. And one way to see that is if you think of this as a measure in the plane, that is a Dirac measure at these 4 points at the corners of a square with plus and minus values, that measure is not detectable by its projections onto the x and the y axis. So that's an example of a function, a generalized function, which can't be recovered by adding up functions of its projections. So this is or dually, it's a measure on the plane that can't be created by pulling back measures from the axes. So this problem of when sets of eigenvalues can be achieved multiplicatively, or eigenvalues or principal values, actually has a curious relationship with the Arnold problem of when functions can be expressed in terms of sums of functions on the coordinates. So, but to kind of close the loop on the idea, what my collaborators and I are doing is we're looking to see when the singular values that pop out when we throw in these trained matrices, when these are largely captured by tensor products of singular values or from smaller operators. And if we find this, that will mean that the rules are obeying rules themselves. These matrices are sort of the rules for human knowledge. And if we find internal structure, tensor structures being one, that would be finding structure within the rules. Here I mentioned my collaborators on this. And I just wanted to mention that there's a school that's been active in France. Lomensky is the name that it's associated with. It's from the 1990s, but still going. It's a school of cognitive science in France that has introduced the words tensor into social science. with terms roles and fillers. And an example of this would be nouns and verbs, like the role, Jill threw the ball. So Jill is the filler that fills the role of throwing. And Slamansky and his school have advocated that there's kind of a hierarchical tensor structure in language starting in the 90s. And when they say tensor, they actually in practice mean direct product of basis sets. They don't actually take linear combinations. But I think that when we're looking at tensors in the context of neural nets, we should use the full mathematical regalia, and we shouldn't just use tensor of linear spaces to mean direct product of their bases. We should really take linear combinations, and I think we can add something that the social scientists haven't there. So I mentioned two directions, and now I'm at the last one and ready to wrap up. So one thing that's replete in machine learning is gradient descent. Everything is about hierarchical order and trying to work your way up the mountain or minimize your loss, ski to the bottom. That seems to be all you ever hear about. But I wanted to point out that there are other orders in the world, and there's rock, paper, scissors. There's cyclic orders. And these are actually very important in ecology. There are papers, there's a Nature paper that you can find using the word collicin. So collicin's a poison, and there are 3 variants of E. coli that can be detected in nature, and one produces collicin to kill its friends, like eucalyptus trees, drop acidic leaves all over the ground so only they can grow. So the collicin-producing bacteria also produce an enzyme that protects them against it so they don't poison themselves. In the general population, you'll find bacteria that produce the poison and the protective enzyme. You'll find resistant ones that only produce the protective enzyme and naive ones that produce neither. And particularly when you're very small, like a bacterium, you can't be good at everything. So if you produce all these complicated molecules, it's a metabolic expense, and you're not going to be able to reproduce as many copies of yourself. So wasted work shows up, and it leads to this cyclic ordering, that the ones that produce the collicin will yield to the resistant ones. These will beat them, but they will yield to the naive ones that don't have the property of producing, don't need to produce anything. And they will, of course, yield, they'll be poisoned by the collicin. So that's like a rock, paper, scissors circle. And on the internet, you can find beautiful animations, and this is just 3 shots. So it's easy, apparently, just to write a cellular automata that has 3 states in it for the 3 kinds. And you just impose the rule, some kind of random rule about you can eat up the other guy's territory if you're ahead of them in the cyclic order. And then they just give it some initial conditions like this. Just draw a few circles and a few lines, and then stand back and let it run. And these are snapshots. So it's kind of interesting. Very quickly, you get about 1/3 of the space occupied by each variety. So you might think, oh, it's achieved an equilibrium. But if you look at it spatially, it's very dynamic. All these spirals are moving around. There's a phrase that ecologists use, 1 million species in every shovelful of dirt. Now, this is just like a call to action or a mantra, because this statement like this should come with an ultraviolet cutoff. As you go smaller, there are more and more species. And then, of course, the idea of species doesn't make much sense when you're talking about whether the offspring are fertile, So, but anyway, it's a rough idea that there's just a tremendous amount of biological diversity. But my interpretation on that is that it suggests that there's something beyond a potential function going on, like these E. coli. Because if all survival is about climbing to the top of some fixed potential function, I'd expect tens or hundreds of winners. I wouldn't expect a million winners, if they all have to be best. It isn't that they have to be best. They just have to have some judo move that beats someone else, and they can have a little place to live for a while. And I think, if we try to understand how the mind works and how artificial agents work, I think we can imagine also cycles, that maybe you have some intuition, but you yield to authority. You're told Bill Thurston's already thought about it and has a different idea. But then you think about it yourself, and maybe you think, oh, maybe I was right after all. But then you think, oh no, this is heading off in the wrong direction. It can't be right. So you kind of go around and around. And I think in the mind there are these cycles. And actually, Kahneman, Tversky wrote this influential paper called Prospect Theory in 1979, which became later a book of Kahneman's called Thinking Fast, Thinking Slow. And they pointed out that there are even like two cycles in your mind, like the grass is greener on the other side of the fence. If you're a horse, you jump over and eat that grass. And so they rejected the idea of a potential function or a loss function. They said there's no way per human in their mind holds this entire tree of possible actions and outcomes and has weighted each one. Instead, you just wait till you have a choice, do or do not, take this action. And then that's a prospect, and you do it or you don't. You decide to go to the other side of the fence, or not. They had a very negative view of human intelligence, by the way. When you read the book, they basically are saying we're all idiots. And I think Kahneman got the Nobel Prize in economics. Basically, it was rather brave of the economists to give it to him, basically for saying all their assumptions are wrong. We're not rational actors. We don't do anything. But actually, there's a very interesting reply, as long as I mention these guys. Mercer and Sperber wrote this book, Enigma of Reason, where they say we're actually rather smart. Our brains just weren't intended to do math or probability. Our brains evolved to get us out of trouble and our linguistic skills. So if someone in your tribe comes up to you and says, you took more than your share of bananas, you have to say, oh, but I'm the great hunter. I needed the energy to bring back. You have to come up with something, whether it's bullshit or not. So they said, for what we use our brains for, they're actually perfect. Okay, so conclusions. I just want to kind of run through the talk backwards very fast. So classical ML seems to have no use for the square root of -1. I've never seen it in classical ML. So with regard to this idea of things going in cycles, I think there might be some way quantum can get involved because we have edge modes and things like that in quantum mechanics. So if you want to get things moving in a circle, it's nice to have that I in there. Okay, that's just a random thought. I know that classical equations can produce a closed orbit too, but I think it's useful to look for emergent structures in all the linear algebra. Machine learning is just applied linear algebra, most of it. And I think tensor structures are one thing, but I'd like to, you could just say, can you dimensionally compress these matrices that come up? Are they highly structured, or are they kind of incompressible in a Kolmogorov sense, Kolmogorov complexity sense? I think we need to understand how dynamics, and probably it's the onset of chaos that's important, how does that make ML work? And can we look at that from 2 points of view? Can we look at dynamics, both quantum and classically? We'll see different things. And then, as I already mentioned, I think this idea of the Arnold Kolmogorov theorem is beautiful, but it needs to be quantified to be of use to machine learning. Thank you.
Thanks for the very inspiring talk. We have time for questions. Also for people on Zoom, you can raise your hand.
I have a question. So in the beginning, you have this representation, but I thought in this deep neural network, it's the sigma is more or less simple and fixed. I mean, and then it was trained the phi, but the theorem statement seems to be the opposite.
Yes.
Speak into the mic. That way people...
Oh, it's too late. I already finished.
Let me repeat Professor Yao's question. Yeah, so, sorry. Yeah, so I think the question was, why is there any relationship at all between this Kolmogorov Arnold theorem, since the nonlinearities in this theorem, the nonlinearities here are these alpha functions, which could have 1,000 laps or something, and the nonlinearities in a deep neural net are these things like ReLU, or that have 1 or 2 laps, something like that. And I think that there's going to be a trade-off, that I think this is an existence theorem. And I think what we'll find is that if you force the network to be short, that the output functions, or the activation functions, have to be extremely complicated. So all the work is complicated, but if you let the neural net have 80 layers, then you can achieve something very similar with a very simple activation function. And that's what I was trying to capture in this conjecture about the French pastry, that the usual activation function is something like that, or maybe has a little dip. But I'm conjecturing that there's a trade-off, that the activation function, if you like, for the Kolmogorov Arnold theorem is much worse than this one. It's some crazy continuous function. And using those crazy functions, you can get away only folding 3 times. But if you were willing to fold 80 times, then you can use a more modest activation function. That's what I'm guessing.
So are there some nice examples of explicit continuous functions in their Kolmogorov Arnold decomposition?
I don't
You can call it that, where we could see examples of what these
Yeah.
Fs and alphas would actually, and 5 PQs would actually look like.
It's not a mystery what the 5 functions look like. And in fact, some of the papers I've found online have some computer drawings of these coordinate functions. What they look like is they can be made, I mean, this was, I think, quite a remarkable thing that they can be made Lipschitz, because since the theorem is sort of contradicting your sense of dimension counting, it would be natural to expect that these functions would have to be Holder continuous, only Holder continuous, like a space-filling curve. The usual construction of a space-filling curve is you split the coordinates, and if you look at what that means, it means that you get like a precision in 10 decimal places in the plane. You'd have to have 20 decimal places precision in the line, because you're using half the coordinates for the x-axis and half for the y-axis. So I think it's a surprise that these functions can be Lipschitz, but what they look like pictorially is they look a lot like the Cantor function. They have flat spots, almost flat spots, maybe a slight tilt, and then sort of infinitely steep to a next small flat spot or nearly flat spot. So I don't think that the explicit representations will be very illuminating. The existence theorems are all through the bare category theorem. You show how to make a very small improvement, and you show that that's an open dense set of functions that make this small improvement, and then you take some intersections, and you get the fully improved limit.
just to get some intuition for, if
Yeah.
what the functions f.
Well, I mean,
If I'm given a function f, what kind of crazy stuff do I get for alpha?
Yeah. I mean, I understand the proof well enough to have some intuition, and it's actually quite interesting where the number 5 comes from, 2n plus 1. It comes from sort of a game theoretic thing. You kind of create a battle between two sides, and one side is sort of ruining your approximation, and the other side is improving it. And it turns out that if you have 3 people on the improving side and 2 on the losing side, the improvers overpower the losers. I mean, so there's a bit of analysis, but so I say my intuition is very low for the outcome, but I understand the dynamical system that finds the functions. Yeah.
So actually, you mentioned 2 things that are very important. So expressiveness of the functions, and also trainability. But there's also this sort of equally important thing that people care about in the subject, which is generalizability. So typically you kind of want the simplest function that fits the data. And I'm wondering if there's I mean, I wasn't familiar with this Kolmogorov Arnold theorem. It's amazing. But yeah, suppose you restrict the complexity of your function. Are there analogs? Somehow these 5 functions that you need to pick to be able to represent any function are going to have to be quite complicated. But in practice, the functions that we're trying to learn are probably not that complicated. So are there versions of this if you simplify you put some kind of bound on the complexity of the functions?
Right. So this generalizability that Ellie is talking about, one way of looking at that is you don't want to overtrain. Is that, would you say? Yeah. The fear is that, in fact, the thing that's remarkable about these large language models working as well as they do is they have so many free parameters, like getting up to 1 trillion free parameters. You'd expect them to be overtrained, that they should not be able to generalize, but they're like stuck in some very narrow minima. So I don't think people really know why the language models generalize as well as they do. So it's hard to say, what aspects of the, how you would tweak the Kolmogorov Arnold theorem to optimize generalization. But what Ellie's asking for is exactly right, I think. It's the right direction. I think this is sort of what I was trying to get at when I said we need a quantifiable version, because we want to know, and it's in the same spirit, I think, as your question about examples, is we want to know if we need the output to a certain fidelity, then how many kinks and curves do these coordinate functions have to have. We know if we make them smooth, we can't do it. But what does can't do it mean? It means that you can't exactly achieve a particular multivariable function. But we should be able to converge, and I think generalizability as well as trainability is going to be an important aspect. So you can ask whether you converge to a function. Just the easiest way to picture as a mathematician is just, do you converge in the sense of being able to represent the function? So that's expressibility. But then a more subtle thing is, given some random training set, will you be able to reproduce with some fidelity after a certain amount of training the function that you're headed toward? So how these behave as a function of the Arnold Kolmogorov embeddings, that's unexplored. That's sort of what I'm asking for when I say quantified version.
So how to consider the quantitative version of the trade-off between trainability and expressivity, like in the dynamical system? Like, can you use the topological entropy of the dynamic system to quantify the trainability or non-linearity in the neural network?
Yeah. So the paper I mentioned where they evolved a circle and you saw it getting very wild. They studied like the expectation value of second fundamental form of hypersurfaces. That was like one of the things they studied, or the variance of, since they were working in Euclidean space, they didn't consider the intrinsic geometry, but it was the extrinsic geometry. So they talk about invariance of various extrinsic measures like sectional second fundamental form, and what they observed was transitions to chaos, what they called chaos in the paper. They didn't establish that it was chaos. They didn't connect, in my mind, to a mathematical definition of chaos, but they definitely found regimes where the curvatures, these normal curvatures, would start blowing up exponentially, and then they associated those with the Lyapunov exponents. By the way, mentioning Lyapunov exponents, one of the advantages of looking on the quantum side of chaos is the classical side is extremely infinitesimal. The definition of Lyapunov exponents, you have to go way back towards zero. I mean, it's how the trajectories diverge at the very start, whereas these quantum measures, like the scarring, they have to do with a longer time scale in the problem, something like the Thales time scale. So they seem to be talking about different things.
But can this argument be generalized to the quantum neural network or quantum machine learning? Because in quantum mechanics, there's another concept called quantum scrambling or optimal autocorrelator.
Yeah. I mean, I think the time order out of order correlator is like probably the most fashionable way these days to understand chaos in quantum mechanics. Yeah, so I think that's a great problem. How to relate the physical knowledge about TOTC to machine learning. What can we do?
Last question.
Thanks for the nice talk. In one of the slides, when you talk about quantum machine learning, you mentioned the possible relation between quantum Fouquet phase and measurement-induced phase transitions to active matter.
Yeah.
Here, the active matter, do you still thinking active matter that has some periodic structure in the time direction or something even more general?
Well, more general, I think of it as kind of matter that's driven. And the simplest way to drive is like Fouquet with some periodic drive. Another very simple way to drive is just to randomly measure stuff. You can do that in the lab, and particularly if you don't have to feedback. But then the more interesting thing is if you drive the thing by some unitary, which is the result of the measurement you just made. So the typical time scale in a lab for this might be a microsecond, perhaps even less in some setups. But you do something, you analyze the measurement, and then you act. You do that maybe every microsecond or 100 nanoseconds. And then there's this concept of measurement-only quantum computation, which is to drive a fully protected quantum computation by a sequence of measurements. The sequence of measurements isn't specified in advance. The next measurement is determined by the outcome of the previous measurements. So if that can be achieved, that's like very highly controlled active matter in this sense. But my point was that we're decades away from making a quantum computer that operates on those principles, or maybe a decade. But right now, we can probably use early quantum computers to explore active matter and the onset of chaos in it. And perhaps we can use that to figure out what kinds of chaos are helpful and what are harmful to a neural network. How So my hope is that maybe some quantum experiments can be used to help design classical networks.
Thank you.
Okay. Well, with that, the next talk is at 11:15, and let's thank Mike again.
Thank you.